Alright everybody, welcome back to Binary Adventure Radare2 tutorial. I'm going to dive straight into solving an actual CTF challenge in this video. So instead of just going on a tour showing navigation in Radare2, we're actually going to use Radare2 to solve a real world challenge. Okay. Um, so the one we're going to solve is this flag right here. So if you go to pwnable.kr, which is shown right here, and then you click on this right here, you will be brought with this screen that says Papa brought me a packed present. Let's open it. And then it says, it gives you this download URL. Okay. So what you're going to do is you're going to paste the download URL up here. You're going to hit enter, and then you're just going to download a binary file. I've already downloaded it, so we're going to get rid of the browser now and go straight into action. So what we know is that the name of this binary is flag, and I know it's in my downloads folder, and that's literally all we know. The browser actually did say that it is a reversing task. So it says this is a reversing task. All you need is binary. So that's what we know. So typically when you do something like this, you want to do sort of an initial recon first. So I'm just going to go ahead and open up Radare2 in order to do this. So I'm going to do R2-AA, and then I'm going to say /flag. And then you'll notice here that there is a bunch of different analysis checks done because AA is equivalent to running AAA. And if you watch closely, you remember from our last videos, there actually were fewer analysis checks done in those last videos, and that's because I recently updated my install of Radare2. So the Ubuntu repository has like version 2.3 or something, and this is actually version 4.2 or 4.3. And one thing to note is that when you do perform these analysis checks, it's doing more work. And one thing I noticed is that with large files, it's significantly slower to analyze. You may be able to get away with just using a AA instead of a AAA, but if you find it slow for a large file, you might actually want to use the older version because there are some interface changes and things, but I haven't found anything that I need to use that's in the new version that's not in the old version yet, but it looks like it's doing more analysis for like C++ stuff like vtables and things like that. So that all aside, what we're going to do now is just try to gather some basic information. So if you hit I question mark, it will kind of remind us of how to do that. So what we could do here is just do a IA in order to get basically all information that could be disclosed to us. So now, because that's a lot of information, what you can do in Radare is you could hit the tilde key and then ... So again, so I'm down here at the prompt at the bottom of the screen, and then I'm gonna hit tilde ... at the end of the command. So it is IA tilde ... and what that's gonna do is basically pipe the output into less so that we don't blow up the buffer of the screen and have to scroll back up and things like that. So now that I'm doing that, we can see here there's actually not much on the screen. So the first thing we notice is that the architecture is x86. It's an ELF. It's 64-bit. There's no stack canaries, and also this is not position independent code, so ASLR probably wouldn't be applied here. And then usually there's imports and exports, but there are no imports and exports listed. Now I'm going to go ahead and get back out of this, and what I'm going to do now is let's see what other type of information we can gather. So let me do AFL. Remember, this binary has already been analyzed, and you can see that Radare did find the entry point in some other functions, but they're not labeled, and it's not like other stuff we were dealing with in previous tutorials. So what this is telling you is that this binary is one of two things. It was either written in like raw assembly language and it's not using any symbols whatsoever, or the more likely option is that the binary is stripped. So what we mean by that is that somebody compiled this file, likely, if they use GCC, they likely compiled it with the S flag. So when you're compiling a C program, you could just go GCC, myfile.c. So myfile.c would be your source file. And then you could do -s and then -o and then myfile. And what this would do is GCC will compile the myfile.c source file, and in the process of doing so, it will strip out all of the strings in the file. It will strip out the symbols, the symbol table, and the exports, the imports, and things like that. It won't strip out strings that are needed for the program to run, but it will strip out all the things that are not necessarily needed, that are sort of used for the developer's convenience, so to speak. So, and that works on GCC. I know that the version on Apple Clang, it won't let you do -s, so you're on your own there. But if you're on Linux and you're using GCC, you can do -s. So that's like a little pro tip. If you are writing CTF challenges, you probably want to strip your binary so you don't give hints and clues away. Okay, so that's very likely what happened here. So another thing we can do now that's pretty common, another piece of information that you're going to want to get is the strings in the binary. So in order to get strings in the binary, we could type IZZ, but again, this could be something that is very long. So let's do the ~. Again. It's a pipe to less. And so we're looking at strings here. It doesn't seem like there's too much going on. We got some strings. But it just, something just kind of seems off. It's just, you see all these things about basic Latin, Hebrew, a bunch of different languages, and other than that, there really isn't anything useful. It just kind of seems to be going on forever. We don't see any symbols. We don't see any references to any C files or any type of functionality. It just something seems off, right? So I'm going to go ahead and go back and run that command one more time and show you something. So let's run the command one more time, and let's pause. The very first line there says UPX bang, or UPX exclamation point. That is a really big clue. This is also kind of interesting too. You might actually be tempted to go and Google that, but this is actually a really big clue. So UPX is basically a compression format for binary files. So think of it like a zip files kind of, but just for binary executables. And what it does is long story short, it instead of creating a zip file where you have to extract a file out of an archive and then run it, you can actually just run this thing in the compressed format, and then at runtime it has a stub which is code that has an algorithm that then unpacks the rest of the file and then runs the file all at runtime after you double clicked on it or after you ran it, right? You can't run a zip file. You would, if it was a zip format or like a tar GZ or something, you would have to like untar and then ungz it, or ungz and then untar it and then run it, right? But with UPX, it kind of is like built into being an executable format, okay? And it's actually, it was commonly used by malware and stuff in the past as well to try to like hide code from antivirus, but antivirus has gotten a lot better with that, so probably not very effective with that anymore, but it's still useful for compression and for CTFs and things like this. So instead of having to go and do a whole bunch of extra work to figure that out, I mean, usually what you'd have to do is probably like Google that, and then you find out, oh, this might be what's going on. So there's a program that you can download just called UPX in the Linux repositories, and I've done that. So let's actually try using that program to unpack this thing. So we'll do UPX-D./flag. and UPX tells us that it successfully unpacked it, and it just overwrote itself. So it's the same file. It's going to be called flag again, right? So now all we got to do is do R2 and then -AA again, and then /flag. And let's just go ahead and load and reanalyze this thing. Okay, so and then Radare is actually giving us a tip saying that if we use this CA command in Radare, we could actually find AES keys in memory, which is pretty cool. We don't need to do that now, but it's just kind of a cool function of Radare2 is to be able to do that. So, okay, so what we're going to do now is go ahead and try to re-examine things. So we'll do I question mark, and then we will do, let's just do IA again. So IA tilde ... And well, okay, so this part is mostly the same. However, check it out. We actually have our exports now, and there's a lot of them. There's a lot of exports listed. So rather than go through all of that, let's go ahead and do I capital I, or I lowercase I, rather. So it doesn't show anything for imports. Let us look at strings now, though. So let's see if there's any difference in the strings. So for that, we'll do IZZ tilde ... And then, okay, so this time we actually don't have the UPX up there. So that shows us that the unpack probably worked. There's still not a lot of useful strings here. If we kept scrolling down, we probably would see more than we did before. But there's not a ton of useful strings there. Now let's just look and see if we have a function list now. And it looks like we do. It looks like we actually do have a function list. And I'm going to follow my own advice here and do the tilde ... Emery map. Let's see if we can find anything useful. I got a lot of stuff. So what I'm going to try to do is just do S main and see what happens. And it looks like we do have a main function, and there it is. So now that we're in the file here, you know, at the main function, you can see what's going on is that it calls puts, and then it calls malloc. So if we actually run this thing, it looks like it is going to print out something to us, and then so it looks like it's going to print I will malloc and stir copy the flag there, take it. So the idea here, let's just go ahead and actually run it, and then we're going to go ahead and start a debug session to actually figure this out. So the idea here, let me do /flag. Okay, so if I run flag, it does exactly that. It says I will malloc and stir copy the flag there, take it. So this might be kind of confusing because if we do this and like say something here, like some of the other CTF challenges you're used to seeing, it's not really taking any type of user input for anything useful. So it's like, how do you get the flag? So basically what it's telling us is that it's going to malloc some memory and then copy the flag into that memory. So now we need to kind of get a handle of the memory and basically view that memory, which means we're going to have to likely, the most efficient way to do this is probably going to be at runtime. So we can use the R2 debugger. So I'm going to do R2 dash d dot slash flag, and we're going to start the file in debug mode, and then I'm going to try to analyze this thing, and it looks like I said before, it's going to be kind of slow, so I'm just going to try to do just AA instead of AAA. Let's see what happens. And it's taking a little while, so I'm going to see if I can get away somehow with just doing AFL, or just going ahead and saying db main to place a breakpoint on main, and then let's actually seek to main, and then let's open it up in visual mode, and it looks like it's calling puts and malloc just like we saw earlier. So, and then it calls some function here. Since there's only 3 functions in the whole program, and we know that it says I'm going to malloc and stir copy the flag there, take it, let's just assume that this right here is the stir copy function being called. So making that assumption, what we need to do is we need to access the memory that is malloced after that stir copy, but before the program ends right here. So we need to really place a breakpoint right here. Okay. And how do you get to the memory that malloc returns? Well, it's going to actually be in RAX, because that's in this ABI, the application binary interface. The return value of a function is placed in RAX. So, and you can see here, that's why it's moving RAX into RBP -8. And so what we're going to want to do is take a look at what is in that area after the call. What's that memory address? And so what we can do in order to facilitate this is also place a breakpoint on 0x0040119A. So I did the colon db and then that memory address. And then all we need to do now is just go ahead and run this program until we hit the breakpoints and kind of step through it. So let's see where we are. Okay, so I hit F9 there. I tried to do a debugger continue command DC, but it didn't work. So I pressed F9, which is like run until you hit breakpoint. And so now we're getting pretty close. So we could actually single step. I'm using F8 here to do a step over. So I'm going to step over the puts, and then I'm going to step over the malloc. And then you can see here that the return is being placed into RBP -8. And then I'm just going to keep stepping over everything. And then I'm stepping over this call. And now, if we assume correctly, we should be in the proper spot. And so what we could do here is try to examine that memory. So let's first do that by going in and trying the command afvd. And okay, it says that we can't find the function. It's probably because we are already, or we haven't, we basically canceled out that analysis step for speed reasons. So I'm going to try something else. So what I'm going to try to do is basically print out. So I'm going to print out PF S at, and then I'm going to say RBP -8. So what this is print function string at, and then RBP minus 8. So let me explain why I just did that. So this is actually useful for you to see because sometimes you're not going to get symbols. Maybe the entire binary is stripped, not because it was packed, but because it was actually stripped and there weren't any symbols. So you would have to figure this out. Now, this binary, if you do actually analyze it and let it go through, I think it takes like 5 minutes or something, then this one does actually have symbols, as we kind of saw earlier. But right now, this symbols didn't get populated for this call here. And it also didn't get populated for the variable name here. So the way that essentially the CPU sees these variables, these local variables, is they're on the stack, and RBP minus 8 is just a stack location. So for example, you had the variable int age in C, then int age could actually resolve to a location on the stack such as RBP minus 8. It's a local variable. So what the process was here was to get the memory address returned from malloc, which is in racks, and then it then is moved from racks into a local stack variable, which for our purposes is called RBP minus 8. So what we need to do would be get that memory address out of RBP minus 8, and then dereference that memory address and view the string there. And that's what this command is doing right here. So if we had actually gone through this with the analysis, this AFVD command should show us the local variables for this function that Radare had found. However, Radare didn't find any yet because we cut it short. And so what we ended up doing was sort of a more primitive or lower level approach, which is this PF command and then capital S. And then at, the at symbol just means at the memory address that we're specifying. And then in this case, the memory address that we're specifying is at the register location RBP minus 8, which is a stack memory address. So this is basically this is basically being replaced, with this memory address here, which is on the stack. In fact, if I go to my other view, I'll show you here in a second. Let me actually I'll show you in a second, but essentially this memory address is what is inside of this RBP minus 8, and then, or it's being replaced. So this memory address is essentially what we are pointing to, or what we're referring to when we're saying RBP minus 8. And then that memory address has another memory address, which is this right here, and that memory address is the pointer to the string here, okay? So we're dereferencing and getting this string out of a variable, a local variable on the stack. And I'll show you what I mean by this. So remember 7FF DC3 F848C8, because if I go here and then I go into debug mode, and then we go to RBP, see it's 7FFDC3 F848DO. So remember, it was when we did this command down here, it is F848C8. And then remember, we're taking that address and we're minusing 8 from it. And then we are getting this other memory address, C8, and then we are essentially dereferencing it to get this string here. And so this is the flag. This is the, so we've solved this CTF challenge using Radare here actually pretty quickly. When I first did this, it took me about maybe 10 minutes to do with Radare, and that's actually including doing the analysis, but the analysis took like 5 minutes, and so I didn't want to sit here and waste a bunch of time, so I wanted to show you that alternate way of doing it. But had we done that actual analysis and gone through with it, then we could use the that command I specified earlier, which is AFVD, which stands for Analyze Function Variables Display, And then usually it wouldn't say cannot find function. It would actually give us the variables that are there by name. And then what we could have done in that case is we could then say AFVD and then var name here, okay? And then once we've done that, what it would do is it would tell us a command that we could use to dereference the memory. So it will actually try to figure that out for you, which is pretty cool. So that concludes this video, and I hope you enjoy. And if you do, don't forget to subscribe, and I'll see you next time.